Today we are going to discuss about the energy band diagram and density of states. In our previous class we have discussed that when we consider a semiconductor, it consists of two types of electrons, free electrons and bonded electrons. And we know the free electrons have larger energy compared to bonded electrons. The energy of free electrons are more and the energy of bonded electrons are less. With this idea, we can now plot the energy band diagram. So now we are going to study the energy band diagram. When we consider the energy band diagram, on y-axis we have energy and on x-axis we have distance. And then we have actually two types of bands. One band is called the valence band and the other band is called the conduction band. When we consider this conduction band, this is the band of higher energy and that can occupy free electrons. And when we consider valence band, this is the band of lower energy and that can occupy bonded electrons. And this is logically correct also, because we know the energy of the free electrons are greater compared to the energy of valence electrons or bonded electrons. And here in this graph we can see as we move upwards from origin, the energy is increasing. So the energy of conduction band is higher than the energy of valence band. So the electrons with higher energy will occupy in the conduction band. That means free electrons will occupy in the conduction band. That is the band with higher energy. And the bonded electrons will occupy in the valence band, which is the band of lower energy. So the bonded electrons or holes will come in the valence band. Now the lowest energy level of conduction band is denoted as EC and the highest energy level of valence band is denoted as EV. So we can say the free electrons have energy greater than or equal to EC and bonded electrons have energy less than or equal to EV. Now the energy gap between EC and EV is denoted as EG and it is called the energy band gap or the band gap energy. So EG is equal to EC minus EV and it is called the band gap energy. Now the probability of finding electrons is 0 in this region between EV and EC. We cannot see an electron in this region and this region is called forbidden energy levels or forbidden energy levels region. The probability of finding electrons in this region is 0. So when we consider an energy band diagram, we can see electrons either in the valence band or in the conduction band. The electrons in the conduction band are free electrons and the electrons in the valence band are bonded electrons. And we know only these two types of electrons are present in the case of a semiconductor. And hence logically also we can say there is no electrons in this region between EC and EV. Now when we consider this energy band diagram, it can take only discrete energy levels. The energy levels present in the energy band diagram are always discrete. So ideally we can draw the energy band diagram like this. As we said earlier, on y-axis we have energy, on x-axis we have distance The band with lower energy is called valence band. The band with higher energy is called the conduction band. And we denoted the lowest energy level of conduction band as EC and the highest energy level of valence band as EV. And as we said here, this energy band diagram can take only discrete energy levels. So the energy levels are discrete in the case of energy band diagram. When we consider the conduction band and also in the case of valence band, the energy levels are discrete. That means when we consider the valence band, if this energy level is E1 and if this energy level is E2 and if this energy level is E3, etc., then electrons with energy E1 will occupy in this energy level and electrons with energy E2 will occupy in this energy level and electrons with energy E3 will occupy in this energy level, etc. And in between E1 and E2 there is no other energy levels present. So it is not continuous. After energy level E1, the energy level present is at E2 and in between E1 and E2 there is no other energy level. So there is no electron in between E1 and E2. So we can say the energy levels can take only specific values, or we can say the energy levels are discrete. This is a very important point. Always keep this in mind that the energy levels present in the energy band diagram are discrete. When we consider the conduction band, here also the energy levels are discrete. Let's say the energy of this energy level is E10, the energy of this energy level is E9, etc. Then electrons with energy E9 will occupy in this energy level and electrons with energy E10 will occupy in this energy level, and in between this there is no other energy level present, or in between this there is no electrons present. So always keep this in mind that discrete energy levels are only possible in case of energy band diagram. Let's now discuss the case of density of states. We know when we consider a semiconductor, in that the current flow is due to the movement of free electrons and bonded electrons. So the number of free electrons and number of bonded electrons or number of holes are important in the case of a semiconductor because they are contributing the current. To find the number of free electrons and number of holes, we need an idea about the density of states. By using this density of states, actually we are going to find the number of free electrons and number of holes present in a semiconductor. And here we are mentioning the density of state for a particular energy level having an energy E, and it is denoted as G of E. So G of E means it is the density of state of a particular discrete energy level having an energy E. Now the density of states is the maximum number of electrons that can occupy at a particular discrete energy level having an energy E in the case of conduction band, and it is the maximum number of holes or bonded electrons that can occupy at a particular discrete energy level having an energy E in the case of valence band. So density of state is the maximum number of electrons that can occupy at a particular discrete energy level having an energy E in the case of conduction band, and it is the maximum number of bonded electrons or holes that can occupy at a particular discrete energy level having an energy E in the case of valence band. So in the case of conduction band, actually we are considering the free electrons, and in the case of valence band, actually we are considering the holes or bonded electrons. To understand that clearly, let's consider this energy band diagram. So here we have distance, and here we have energy, and this is our conduction band, and this is our valence band. Let's consider a particular energy level in the case of valence band, which is having an energy E. Now the density of state for this energy level is denoted as G of E, and in this particular energy level, how many maximum number of holes or bonded electrons can occupy is density of states. If we have another energy level E1 here, then its density of state is denoted as G of E1, and it represents the maximum number of bonded electrons that can occupy at this energy level E1. Similarly, when we consider the conduction band, consider two different energy levels having energy E2 and E3. The density of state for this energy level E2 is denoted as G of E2, and the density of state for the energy level E3 is denoted as G of E3, and this G of E2 represents the maximum number of electrons, free electrons, that can occupy at this energy level E2, and this G of E3 represents the maximum number of electrons, the maximum number of free electrons that can occupy at this energy level E3. That is the concept of density of states. Now, when we consider this density of state, it increases as we move deep into the conduction band, and also it increases as we move deep into the valence band. So the density of states increases as we move deep into conduction band and valence band. To remember that, consider this graph, consider this energy band diagram. So this is our EC level, and this is our EV level. Now when we consider the density of state, the density of states increases as we move deep into the conduction band, and also the density of states increases as we move deep into the valence band. Or we can say the density of states increases as the energy increases in the case of conduction band, and the density of states increases with decrease in energy in the case of valence band. Now let's think why the density of states increases with increase in energy in the case of conduction band, and why the density of states increases with decrease in energy in the case of valence band. Let's first consider the case of valence band. We know the valence band consists of bonded electrons, and the energy of the bonded electrons are less compared to that of free electrons. And we know if the energy of the bonded electron increases, if we supply additional energy to the bonded electron, then that bonded electrons will break the bonds and it will become free electrons, and it will move to this conduction band. And in opposite sense, we can think if the energy of the bonded electrons are very less, then it will remain as bonded electrons itself. So as the energy goes on decreasing, the probability of finding bonded electrons are more, because at lower energies that electrons will remain as bonded electrons itself, and hence at lower energies the probability of finding bonded electrons are more. That means the density of states increases with decrease in energy in the case of valence band. Now when the energy of an electron increases, it will break the bond and it will become a free electron. So as the energy goes on increasing, the probability of finding free electrons is more. So the density of states increases with increase in energy in the case of conduction band. To remember this, we can consider a diagram like this. Consider that energy band diagram. So here we have energy and here we have distance. And this is our EV level and this is our EC level, and we know the density of states increases with increase in energy in the case of conduction band, and the density of states increases with decrease in energy in the case of valence band. So here if we have only one density of state, then in the above energy level there will be more density of states. Okay, so say here we have two density of states and here we have density of states 3 and above we have density of states 4, etc. And similarly in the case of valence band, say here we have density of state 1 and here we have 2 density of state and here we have 3 density of state, etc. Okay, so always keep this in mind that as we move deep into the conduction band and valence band, the density of state increases. That means as the energy increases in the case of conduction band, the density of states increases, and as the energy decreases in the case of valence band, the density of states increases. Now with the idea of density of states, we can find the number of electrons present in a particular energy level. For that, we need to use the idea of probability also. We know what is the mathematical definition of probability. We know the probability of an event A is equal to NA divided by N, where N is the total possible outcomes or the maximum possible cases. And if in that N possible outcomes, if in that total N possible outcomes, NA of them belongs to event A, then probability of A is equal to NA divided by N. So this NA is the actual case, the actual outcomes that belongs to event A, and N is the total number of possible outcomes. So actually probability means the actual value divided by the maximum possible value. So here if we consider an energy level having an energy E, then the probability of finding an electron in this energy level E is equal to the actual by maximum case. That means actual number of electrons present in that energy level E divided by the maximum possible case, and we know the maximum possible case is our density of states G of E. So the probability of finding an electron in an energy level E is equal to N of E divided by G of E, where N of E is the actual number of electrons present in that energy level E and G of E is the maximum possible electrons present in that energy level E, and that is our density of state. Now if we know the probability and density of state, using that we can find the actual number of electrons present in that energy level. That is N of E is equal to P of E into G of E. So if we know the probability of finding an electron in a particular energy level E and the density of state for that energy level E, then P of E into G of E will give the actual number of electrons present in that energy level E. So now we have an idea about the density of states. In our next class, we will study this probability of finding an electron in an energy level E. Then by using that probability and density of state, we can find the number of electrons present in a particular energy level E. So now I am winding up this class here. In our next class, we will study this probability of finding an electron in an energy level, and that is actually called the Fermi-Dirac probability function. Okay, thank you.